Bismillahirrahmanirrahim. We continue our topic about radiopharmaceutical and radiolabelling. In the second video, we will further discuss about methods of radiolabelling, factors in labeling, specific methods of labeling, radioiodination, labeling with the 90M technetium. Method of the radiolabelling. The use compound label with the radionuclides has grown considerably in the medical, biochemical, and related field. These methods and various factors affecting the label compounds, they are isotope exchange reaction, foreign label, labeling with a biofunctional chelating agent, biosynthesis, recoil labeling, and excitation labeling. Have a look at the isotope exchange reaction. Basically, in the isotope exchange reaction, one or more atoms in the molecule are replaced by isotopes of the same element having different mass number. Since radiolabel and the parent molecule are identical except for the isotope effect, they are expected to have the same biological and chemical properties. For example, is the T3 and T4. This is the structure of the T3, and these labeling reactions are reversible and are useful for the labeling iodine-contained material with the iodine radioisotope and for labeling many compounds with the tritium. Next is the introduction of the foreign label. In this type of labeling, a radionucleus is incorporated into a molecule that has a known biological role, primarily of the formation of covalent or coordinate covalent bond. The chemical bond is formed by chelation, and look at the sample is the 99MTC with the albumin, 99MTC with the DTPA, and the radionucleus of chromium with the red blood cell. This is the sample of the research for the introduction of foreign label in the type of labeling. Labeling with the bifunctional chelating agent. In this approach, a bifunctional chelating agent is conjugated to a macromolecules such as the protein, antibody, and so on the one side, and to a metal ion such as the technetium by chelation on the other side. This is the sample of bifunctional chelating agent like the DTPA, and this is the structure of DTPA. Next, there are two methods of labeling actually. The preformed 99TC chelate methods and indirect chelator antibody methods. In the preformed 99TC chelate method, 99MTC chelates are initially preformed using chelating agents such as the diamidodithiol, cyclam, and so on, which are then used to label macromolecules by performance bond between the chelating agent and their protein. In contrast, in the indirect methods, the bifunctional chelating agent is initially conjugated with the macromolecules, which is then allowed to react with a metal ion to form a metal chelate macromolecule complex. Other method is the biosynthesis. In the biosynthesis, a living organism is to grow in the culture medium containing the radioactive tracer. The tracer is incorporated into the metabolites produced by the metabolic process of the organism, and the metabolites are then chemically separated. For example, vitamin B12 is labeled with the cobalt by editing the tracer of the culture medium in which of organism Streptomyces griseus is grown. Another sample of biosynthesis include the 14C labeled carbohydrate. protein, and fat. Next is the recoil labeling. Recoil labeling is of limited interest because it is not used on the large scale for the labeling. In the nuclear reaction, when the particles are emitted from the nucleus, recoil atom or ion are produced that can form a bond with other molecules present in the target material. For example, is the compound to be labeled in the mix with the lithium salt and irradiated in the reactor. The last one is the acitation labeling. Acitation labeling entails the utilization of the radioactive and highly reactive hydrogen ion produced in the nuclear decay process. During beta decay or electron capture, energy charged ions are produced that are capable of labeling various compounds of interest. This is the example. This is the overview table or essential 6 major methods employed in the preparation of the label compound for the clinical use. The majority of radiopharmaceuticals used in the clinical practice are relatively easy to prepare in the ion, colloidal, macroalgebraic, or chelated forms, and many can be made using commercially available kits. Several factors that influence in the integrity of label compound should be kept in mind. So these factors are efficiency of labeling process, chemical stability of the products, denaturation or alteration, isotope effect, carrier-free or no carrier added states, storage condition, specific activity, radiolysis, purification and analysis, and shelf life. Efficiency of the labeling process. A high labeling yield is always desirable, although it might not be attainable in the many cases. However, a lower yield is sometimes acceptable if the product is pure and not damaged by the labeling methods. Chemical stability of the products. Stability is related to type of bond between the radionuclide and the compound. Denaturation and alteration. The structure or the biological properties of the label compound can be altered by various physicochemical conditions during a labeling procedure. The isotope effects result in a different physical and perhaps biological properties due to difference in the isotope weight. Carrier-free or no carrier-added state. Radiopharmaceuticals tend to be absorbed on the inner wall of the container if they are in the carrier-free or no carrier-added state. The other important factor is the storage condition. Many labeled compounds are susceptible to decomposition at a higher temperature. Like protein and label dye are degraded by heat and therefore should be stored at the proper temperature. Specific activity is defined as the activity per gram of the label material. In many instances, high specific activity is required in the application of a radiolabeled compound, and appropriate methods should be devised to this end. In radiolysis, many labeled compounds are decomposed by radiation emitted by the radionuclides present in them. Purification and analysis. Radionuclide impurities are radioactive contaminants arising from the method of the production of radionuclides. The removal of the radioactive contaminant can be accomplished by various chemical separation methods, usually at the radionuclide production stage. A label compound has a shelf life during which it can be used safely or its intended purpose. The loss of efficacy of the label compound over a period of time might result from the hydrolysis and or chemical decomposition depend on the physical half-life of the radionuclide, the solvent, and the additive, the labeler molecule, and the nature of emitted radiation, and the nature of the chemical bond between the radionuclide and the molecules. Now let's move to subtopic specific method of labeling. In the nuclear medicine, the two most frequently used radionuclides are the 99 technetium and the 131 iodine. The 99M TC labeled compounds constitute more than 80% of the radiopharmaceutical used in the nuclear medicines. The rest is the iodine labeled compound and other nuclides. Now we look at the iodine's chemistry first. The iodine is an element belonging to the halogen group 7A. The atomic number is the 53 and the only stable isotope is the 127 of the mass iodine. Of all iodine isotopes, 123 iodine is more suitable for the in vivo density procedure because it has a convenient half-life 13.2 hours and photon energy and give a low radiation dose to the patient. Iodination of the molecule is the governed primarily by the oxidation state of the iodine. Commonly, iodine is available as the sodium iodide and the iodine negative oxidized to iodine positive by various oxidation agents. The hydrated iodinium ion and hypoiodous acid are believed to be iodinating species in the ionization process. So I can here for the iodinium ion and the hypoiodinous acid. Iodination occurs by electrophilic substitution here of the hydrogen ion by an iodinium ion in the molecule of interest, or by nucleophilic substitutions, or we call the isotope exchange. There are several methods of iodinations, which is radioiodide methods, iodine monochloride methods, chloramine T methods, electrolytic methods, enzymatic methods, conjugation methods, demethylation methods, iodinogen methods, iodobring methods, and radioiodinated compounds. We will discuss some of these methods. The triiodide method essentially consists of adding a radioiodine to the compound to be labeled in the presence of the mixture of the iodine and the potassium iodide, whereas the H is the organic compound being labeled, and the yield should be 10 until 30%. Iodine monochloride methods. The iodine monochloride methods, radioiodine is first equilibrated with the stable iodine in the iodine monochloride in the dilute acid chloride, and then the mixture is added direct to the compound of interest for labeling at the specific pH and temperature. So the yield of 50 until 80% can be achieved by this process. So the next is the chloramine T methods. Chloramine T is the sodium salt of N-monochloroparatoluene sulfonamide, and it is the mild oxidation agent. So in this methods of iodination, the first compound for the labeling and then chloramine T are added to a solution of the iodine sodium iodide. So this is the structure of the chloramine T, and the labeling efficacy can be very high, about 90% of yield. Electrolytic method. Many proteins can be radioactivated by electrolytic methods, and the yield almost 80% can be achieved. The enzymatic method. In the enzymatic methods, iodination enzymes such as the lactoperoxidase and the chloroperoxidase and the nanomolecules quantity of the peroxides are added to iodination mixture containing radioiodine, and the compound to be labeled. So the yield should be get 60 until 85% of yield, and high specific activity can be obtained for these methods. So this is the sample of method. Conjugation method. In the conjugation method, initial compound N succinimidyl 3,4-hydroxyphenyl propionate NHPP is the radioiodinated by the chloramine T methods and separated from the reaction mixture. This is the structure of NHPP. The proteins are labeled by this agent by allowing it to react with the protein molecules, resulting in the amide bond with the lysine group of the protein. So the labeling yield is not very high. Let's talk about the labeling with the 99-MTC. As Prof mentioned, more than 80% of the radiopharmaceuticals used in the nuclear medicine are 99-MTC labeled compounds. The reason for the such a preeminent position of the 99-MTC in the clinical use, it is favorable physical and radiation characteristics. The 6 hours physical half-life and the small amount of the electron emission permit the administration of the mini-Curie amount of the 99-MTC radioactivity without significant radiation dose to the patient. In addition, the monochromatic 140 keV photon are readily collimated to give image of superior spatial resolution. Furthermore, 99-MTC is readily available in the sterile, pyrogen-free, and the carrier-free states from the 99 molybdenum and 99-MTC generators. This is the overview of the chemistry of the 99-TC or technetium. This is the electronic structure of the neutral technetium atom and can exist in the 8 oxidation stage. Chemistry of the 99-MTC. Most of the information regarding the chemistry of technetium has been obtained from the 99-TC. Because of the difficult problem in the assessing 99-TC chemistry, principle of the dilute solution play important role in the chemistry of the 99-TC because the concentration of the 99-TC in the 99-MTC radiopharmaceutical is very low. So, for example, 20 ml 3 Curie 111 gigabecquerel sample of the 99-TC eluted from the molar generator only has about 2.8 times 10 exponent minus 7 molar 99-MTC. So 99-MTC radiopharmaceutical is further complicated by the presence of the 99-TC. Reduction of the iron pertenatite. Obtained from the molar generator in the sodium pertenatite compounds has the oxidation state 7+ as configuration of the pyramidal tetrahedron. Reduction of the iron pertenatite by reduction agent stainless chloride, stainless citrate, stainless tartrate, concentrated acid chloride, sodium borohydride, dithionyl ferrous sulfate. This chemical reaction in the reduction of the technetium by stainless chloride in the acidic medium and editing to equation above has 1. Reduced 99-MTC species are chemically reactive and can react with the wide variety of kinetic agents to form technetium chelate complex here. Hydrolysis of reduced technetium and tin. There are possible that reduced 99-MTC might undergo hydrolysis in the aqueous solutions In this case, reduce 99 MTC react with the water to form various hydrolyzed species depending on the pH, duration of hydrolysis, and the presence of the other agent. Hydrolysis completed with the chelation process of the desired compounds thus reduce the yield of the 99 MTC chelate. Hydrolyzed species can interfere with the diagnosis test in the equation if they are present in the large quantity in the radiopharmaceutical. The disadvantages use stainless chlorides. Stainless iron also readily undergoes hydrolysis in the aqueous solution at the pH 6 to 7 and form insoluble colloid. And this colloid bind to reduce 99 MTC, thus compromise the labeling yield. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.